Right. I thought I'd make a short video. Now, I've been testing my miniature. In the previous video, you saw me making my miniature Concentric 6. Now, what I'm doing is running some tests, and I actually found something rather interesting. Actually, I connected it. I've got the Alnico, which I'm flipping at about God, I can't see it on the scope right now. Pulse width 260, 260. Hang on, let's go look at this on the scope. Now, this is what's interesting. Right, we're on this oscilloscope. Now, I'm driving. I've got the probes backwards at the moment. Now, peak to peak, I'm driving the actuator coil. Actually, that's the driver circuit, but I'm driving it at about 60 volts. Actually, it doesn't show up on here. The pulse width is 260 microseconds, right? Meaning 1.2 zone. And the secondary. Now, this is where it gets interesting. No, there's no decimal point there. The frequency on the secondary is 1.428 kilohertz, and pulse width is 360 microseconds. Now look at that's the interesting part. 300 volts peak to peak. Yeah, wow. Now I'll explain. Now this is the waveform. Now this is the waveform on the secondary, and the primary waveform is that, right? Is that little blue blip, right? And that blip is 260 microseconds, right? And I'm currently consuming about 80 milliamps, right? I'm driving the coil at about 80 milliamps. This is the range that I'm on. Now the secondary range is on the 100 volt range, and as you can see, we've got a nice ring there. Now it's because I've got a capacitor. I've actually added a capacitor across the secondary because otherwise it works a lot better. Now I've got the capacitor connected to these white leads. Right, there's two capacitors actually, 200 nanofarads, and they're connected across the secondary. These two white leads are running around here, all the way around to the secondary. And yeah, I was actually quite surprised actually how well this is working really. I mean, I'm not getting a lot of current though when I short it out on my meter. But that's probably because my meter doesn't register too well on that frequency, because it is very ripply, as you saw from the waveform. It's very there's a lot of noise on it, so it's difficult for my meter to register at that frequency. But yeah, I'm going to do some more tests later on. I'm going to hook it up to my rectifier, and I'm going to charge up some capacitors, and then I'm going to see if I can drive the LEDs, which are currently on the other thing in the other room, which I've got to take off. But yeah, I'm glad I built this tiny little thing. Yeah, it's basically my C6, which you can see how tiny this thing is. Right, there's two of them on there, and the Alnico's in the middle. And it's basically based on my larger C6, which is this thing here. This really big thing here. Basically the same principle with the concentric magnets around the perimeter. So yeah, very interesting. So you can see the difference between this thing and that little thing. There's two of them. Anyway, yes, very interesting results, as you can see from the oscilloscope. Now, I'll change the frequency a bit. Actually, let's look at the voltage on it on the meter. My pot's a bit mucky. Well, the voltage on the oscilloscope has actually gone up now. Let's have a look again at the oscilloscope. The voltage now on the output is 336 around a peak, 338. Maximum, I assume that's the mean, 160 volt. 380, 360 microsecond. Obviously, as I reduce the frequency, the pulse width will get bigger. Yeah, and that's the output right now. So yes, very interesting. I was actually working on another new design, which I haven't built yet, which using these magnet holders, but I decided to go ahead with my smaller version because this is clunky. It uses my big laminations and it's harder to fiddle around with. But basically, 2 Alnico bobbins go in there. Now, there's actually 3 Alnico magnets in each bobbin. And there's a reason why I'm going with this little thing, and that's because it's simple. It's just 1 Alnico magnet in the middle, and it makes it a lot easier to experiment with and try out things and get some ideas. But my block diagram basically is this. I mean, this is the model actually. But those are the actuator coils. And actually some magnets go inside this core here, and there's some magnets from the outside going down with laminations in between, and these are the secondary coils. Now, well, based on what I'm finding with this thing, I might actually scrap that. I might not even bother to build it. I might actually work with my laminations running across top and bottom, which are easy enough to do. And because I found out by using different ferrites on the top, I can change the actual output on here quite easily. I've got different ferrite bars, and if you look, if I swap this bar out, take that off, the voltage drops right down then. Now if I stick a different bar on, right, we have lost a lot of voltage. So it needs to be tunable. So obviously I can do that with my laminations because I can insert different amounts of laminations in. So yeah, so I'm using ferrite at the moment, ferrite rods on this thing. So yeah, I don't know if you can hear me or not actually, because this thing's making a lot of noise. But we're only drawing about 50 milliamps. My MOSFET driver circuit, which I'm using, which I used before, which I designed and built, is working very well. It's stone cold. It's actually, there's no heat from it at all. See, it's blinking away there, blink, blink, blink. And the current is actually 100 milliamps, but the circuit uses, the actual driver that steps up the voltage uses 100 milliamps. So it will show 200 milliamps, but I'm actually only using about 90 milliamps. Because when I disconnect this circuit here, this boost converter down here, it's upside down, sorry. This boost circuit uses 100 milliamps quiescent current even when it's not doing anything, so I've got to subtract that. Anyway, I just thought that was interesting. Thanks for watching.